So this is a video on how to attack solubility curve problems. The first thing you need to know about solubility curves are what the curves represent. So to start off with, a typical solubility curve is going to basically show the amount of solute in grams that will completely dissolve in 100 grams of water. 100 grams and 100 milliliters of water are equal to each other. So sometimes you'll see the unit of water as grams or milliliters since they're equivalent to each other. Now, the solid line is going to show a saturated solution. Whenever you see the actual curve, that represents a saturated solution. If the amount of solute dissolved is above the line, it's a supersaturated solution. And then if the amount of solute dissolved is below the curve, then that represents an unsaturated solution. So let me show you what some solubility curves look like. These are the solubility curves, and this is an example of a solid line. Now, this solubility curve kind of looks overwhelming because we actually have 9 different curves in one, but let's just focus on one curve at a time. So if we focus on this sodium nitrate curve right here, just kind of block out the other curves from your sight right now. Any point along this line basically represents how many grams of solute, how many grams of NaNO3 in this case, are dissolved per 100 grams of water. So as you can see, as temperature increases, when the substance gets hotter, when the water gets hotter, you're actually able to dissolve more solute, more sodium nitrate when the water is hotter, just like what you guys saw in the gizmo. Now, if I gave you an intersecting point that falls anywhere above the line, so anywhere in this space here, that represents a supersaturated solution, assuming all of the solute has dissolved. And if I gave you an intersecting point that falls anywhere under the curve, so anywhere else on this graph here under the curve, that would represent an unsaturated solution. Basically, that tells you that you are able to dissolve more solute if I gave you an intersecting point below that curve. Now, that's only for sodium nitrate. You can see each of the other curves have their own pieces of criteria, but that was just for sodium nitrate. Here's an analogy. If you think about a good recipe for Kool-Aid, Kool-Aid is a powdered drink, lots of sugar, yummy goodness. And if you think about the serving size for a good recipe for Kool-Aid, you might think about the amount of water being 100 milliliters. So let's say we have a little glass of Kool-Aid, it's 100 milliliters, same thing as 100 grams. If we were considering a solubility curve, basically the perfect amount of Kool-Aid would represent a saturated solution. The perfect amount of Kool-Aid would represent a saturated solution, so any point among that line. But what you guys should know is that when you make the water hotter, so this statement here says when you make the water hotter, you can actually dissolve more Kool-Aid into the water itself. So if we think about our Kool-Aid powder over water as being like a ratio, this represents a solute over solvent. An unsaturated Kool-Aid solution would be like a light pink Kool-Aid solution, and we all know what that tastes like. It's watered down, it's too dilute, and so there's not a lot of solute involved. This is not a perfect recipe. It's an unsaturated solution. Unsaturated means unfull. A saturated solution would be like the perfect amount of Kool-Aid. It tastes great and everything. And finally, a supersaturated solution would be like a Kool-Aid solution that's way too sweet. In an actual scenario where you're making a supersaturated solution, remember that in order to properly make it, you actually have to heat up the water and then cool it down very slowly. And that's the only way to get an actual supersaturated solution. So here are some solubility curves again. You can see there are different substances on this curve, on this graph, and let's see. Here are some little tips for solving solubility curve problems. Whenever you obtain a value from the solubility curve, the actual curve itself, it's always for a saturated solution. It always describes the grams of solute per 100 grams of water. So don't divide the numerator by the denominator. We want to make sure that denominator stays 100 grams because it's per the amount of water. If we are noticing that in the problem 100 grams of water is not used, you can just set up a proportion. This is basically representing out of 100 grams of water like 1 glass of Kool-Aid or 1 glass of solute, and then you can set up a proportion to change the quantity of water. Let's say you're trying to make a pitcher of Kool-Aid. So you can set up a proportion pretty easily for that. Just remember that 1 gram of water is equal to 1 milliliter of water because the density of water is 1 gram per milliliter. And now here's a real problem. I have a solution at 60 degrees Celsius with 80 grams of sodium nitrate dissolved in 100 grams of water. Is it saturated, supersaturated, or unsaturated? So with this problem, we're going to focus on sodium nitrate, which is the line I pointed out earlier. So here's sodium nitrate. We're going to notice what the x and y axis give us. The x-axis is temperature. The y-axis is the grams of solute. So let's find 60 degrees Celsius, which is right over here. 60 degrees Celsius. And 80 grams of sodium nitrate is dissolved in it. So 80 grams would bring us up to this point right over here. Now this intersecting point falls below the curve. The intersecting point falls below the curve, therefore it is an unsaturated solution. So there's our curve, here's our intersecting point. Now the point at which these two values intersect fall below the curve, which means the solution is unsaturated. Unsaturated tells us we could potentially dissolve more sodium nitrate into this solution to get it to the saturation point. We would be able to dissolve 10, 20, 30, 40, about 44 more grams of sodium nitrate to reach that saturation point, that point where it's too full and cannot dissolve anymore. And I kind of just answered that next question in this case. So we have our intersecting point, our unsaturated solution, and if we wanted to reach a saturated solution, we're basically trying to see how much more solute could dissolve. So right now there are 80 grams of sodium nitrate dissolved according to the previous problem. You can rewind it to the video if you need to see that. And we can dissolve 10, 20, 30, 40, about 44 more grams of solute to reach the saturation point. Here's another problem. We want to see how many grams of potassium nitrate will dissolve in 300 milliliters of water. Now, I see a red flag in this problem. The red flag comes with the 300 milliliters of water. We have a graph that only represents our amounts of water in per 100 grams. So we want to make sure to set up a proportion. So whenever you see an amount of water that is not 100 milliliters or 100 grams of water, that's a red flag to set up a proportion. And here's what our proportion can look like. We have some information on our graph at 50 degrees Celsius. So 50 degrees Celsius, let me back up a little bit. Here's 50 degrees Celsius, and we can see where the saturation point is for potassium nitrate. Potassium nitrate is KNO3, and even if you didn't know it was KNO3, you could almost guess between these two formulas that both start with potassium. We see nitrogen in this formula, so we can almost just guess this is potassium nitrate if you weren't sure of the formula. We're focusing on this curve here. I went to see where the 50 degrees Celsius intersects with the potassium nitrate line, and I did that because it says how many grams of potassium nitrate will dissolve. Will dissolve basically means it's saturated at this temperature. We can dissolve 80 grams of potassium nitrate if the temperature of the water was 50 degrees Celsius. That's what our point shows us. So I want to set up a proportion to say how much potassium nitrate can dissolve in 300 milliliters of water if I know that 80 grams dissolves in 100 grams of water. So I got the 80 from my graph to see where the intersecting point is with 50 degrees Celsius. I can do some cross multiplication here. 80 times 300 divided by 100. And that gives us 240 grams of potassium nitrate. Next up, I have just a little visual to give you an idea of how we were able to solve that problem using a ratio, a proportion. Now, what we got from the graph is that 80 grams of potassium nitrate is able to dissolve in 100 grams of water. So basically, we are multiplying that value by 3. It's like we had 3 servings of this potassium nitrate drink at 50 degrees Celsius. So that's where we got the 240 from, because 80 times 3 is basically the proportion here. 80 times 3, 100 times 3, and that's where we got the 240 grams from. To see a different problem, I have a saturated solution with 9.2 grams of solute dissolved in 10 grams of water at 25 degrees Celsius. What is the solute? So this is a different problem because we're actually trying to identify which one of these solutes we're dealing with, and we see some key words here. We see it dissolved, and dissolved means it's saturated, that it's perfectly saturated with the perfect amount of solute. Now, there's a red flag going on in this problem. The red flag comes with the 10 grams of water, because we can only solve problems over 100 grams of water because that's what our graph gives us. So let's go ahead and set up a proportion. As we start to solve the rest of the problem, we can go ahead and set up our proportion, and our proportion is going to be the amount of solute over the amount of water. So 9.2 grams of solute over 10 grams of water according to the problem, and now we can set up that proportion to see how much solute will be in 100 grams of water. This is just a proportion, and you can actually eyeball this proportion a little bit because we can see that 10 times 10 is 100, so 9.2 times 10 is 92 grams. So our amount of solute that can dissolve per 100 grams of water is 92 grams. 92 grams is going to be the Y value on our graph here. So 92 is right about here. And we do see that the water is at 25 degrees Celsius. So 25 degrees Celsius would be right about here. And we actually intersect with a line of sodium nitrate again. So sodium nitrate is saturated at that point. So the solute is sodium nitrate because that's the point that intersects between 92 grams and 25 degrees Celsius. As we look at this graph, this question says, what substance appears to be a gas and how do you know? Well, if you're just playing the odds, this is a great test-taking strategy. Try to find something that doesn't belong, kind of like that Sesame Street game. If you look at all of the curves are in the positive slope direction except for one. This one right over here. You can see it's in a negative slope direction, and that just happens to be the gas. NH3 is a gas, and the reason why it's a gas is because gases are actually more soluble when it's cold. So here are the cold temperatures. We can see the solubility is at its max, and solubility decreases with increasing temperature.